a 3 to 5-year-old. You get a picture. There may be enough so you can even have 2 and take 1 home. But the kids worked very hard on this. And then my daughter Kayla actually had veto power over the pictures. She thought some of the pictures did not do a good job, and she actually told me I could not use some of the pictures for the class. How many of you have actually seen paper like this before? You actually had to align it on the little wheels with the spokes coming out to print out. Okay. How many are excited about the exam quest, whatever, not Monday next week, but the week after that, the 18th? All right, well, there's still plenty of time to get excited about it, don't worry. So it's going to be on basically Chapter 11 plus Calc 1, Calc 2. All right, so this is a chance to just get an assessment of how you're doing, how's your preparation. Friday's class will be a review session for the exam. Okay, so what I want to do is I want to stay indoors today if possible. There was a fire alarm at 10. Sadly, there's often a correlation between 1 fire alarm and 2 fire alarms. So hopefully we will not have to go outside. If we do, the lecture continues outside. We will all go basically back in that way over there, and we will continue to speak. All right, so what I want to do now is I want to do section 11.3, properties of the cross product. So we did a lot of stuff on the cross product before. So there's a few things I wanted just to talk about. So 11.3, properties of the cross product. So can someone tell me, what does the cross product take as input, and what does the cross product give as output? What do we have? Cross product takes what as input? 2 vectors as input, and what does it give as output? Yes. A vector as output. This is different than the dot product. The dot product takes 2 vectors as input and spits out a number. The cross product spits out a vector. Now the dot product was commutative. P dot Q was Q dot P. For the cross product, we actually have P cross Q is minus Q cross P. And if you think back to the definition of the cross product, it's related to the signed area, the signed volume. If you switch the order of things, you're going to switch the sign. If you think to the expansion, when we took the determinant and we had the P2 Q3 minus P3 Q2 I hat plus blah, 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 blah. If you switch the order of P and Q, you're going to multiply each component by a -1. So P cross Q is going to be in the opposite direction as Q cross P. An immediate corollary of this is P cross P is 0, because it has to equal the negative of itself. All right. A really interesting one is that P cross Q is perpendicular to both P and Q. So what we saw at the end of class last time was not a miracle. It was not just a wonderful alignment of numbers from a made-up example, but actually a general principle. And so what's nice about this is, one way to see this is the roll up your sleeves, brute force algebra. I know what P is, I know what Q is, I can calculate P cross Q, I can take the dot product with P, I can go through all the algebra, and I can see it's 0. This is not really illuminating, but it is a way to attack it. I'm going to try to show you a better way, a more geometric way of doing it. Sadly, of course, to really understand this way, what class do you need to know? Linear algebra, right. Basically, it's like a broken record. Okay, when in doubt, you need linear algebra. All right, triple product identity. So A dot B cross C is the volume of the parallel pipette formed by A, B, and C. So if you think about what's going on, here's B, here's C. This is related to another nice property of the cross product. B cross C is, so let's do, the length of this is the length of B, the length of C, times the sine of the angle between them. Well, what is the geometric interpretation of length of B, length of C, sine of angle? What's this geometrically? We've seen this before. Yes? Base times height. I love drawing auxiliary lines. If I draw an auxiliary line here, oh, this thing over here is C sine theta, or length of C sine theta. This is the area of the parallelogram that B and C form. So B cross C as a vector, it has magnitude and it has direction. The magnitude is the area of the parallelogram that B and C form. The direction turns out to be perpendicular to B and C. So it's going to come straight up like this. One way to see this, or to build an intuition for this, is to take special cases. So you can take something in the I direction, something in the J direction. And so since the other class, well, I'm inside, I don't have to. So here's I, here's J. And it turns out I cross J is equal to K, coming up straight like this. I can also look at J cross I. I'm sorry, J cross K. I'm going very carefully, I'm going in a cyclic order. J cross K, if you do the calculation, turns out to be I. And the last one, going in the same order, is K cross I, turns out to be J. And it's the same picture as before. So now I want K first, then I, and I get J. What's really going on is this is known as the right-hand rule, or the right-hand screw rule. Not that you're screwed, it's actually giving you the way to remember what's going on. You take your fingers, and I do apologize for those who are left-handed, you take your fingers and you point the fingers in the direction of P. And you have your thumb pointing up like Fonzie, if you remember who he is. You swirl your hand in the direction from P to Q. Okay, so she's like little fishes now going on in there. So you move it from P to Q, and your thumb points in the direction of P cross Q. So if you look at I cross J, I is this way, J is this way, I cross J is pointing up to K. If I look at J cross K, again, this is now going to point in the I direction. The last one's a little painful. K cross I comes down like this, points in the J direction. So if you take some special cases, you can see that the cross product of I and J is perpendicular to I, it's perpendicular to J, it's coming up in the K direction. How do you prove the perpendicularity in full generality? Well, we have the algebra proof, and the question is, can you try to find a more geometric and nicer proof that P cross Q is perpendicular to both P and Q? All right, well, this does have a lot of nice implications. Because B cross C has this wonderful formula, the length of this vector is the area, the direction is perpendicular to the plane. Now a formula like this, again, you can prove it by brute force, it's a reasonable formula. If I double B, what should happen to the length of B cross C? So if I double B, what should happen to the length of B cross C? We've got a guest from here. We've got to show them what William students are like. If I double B, what happens to the length? Doubles, right? If I quadruple the length of C, what happens to the length? Quadruples. So whatever the answer is for the length of B cross C, I've got to have a length of B, length of C. And then I have something complicated involving the angle. And it's not immediately clear that it should be sine of theta, but something like this passes the smell test. I've got a length of B, I've got a length of C. Let's go back to the triple product formula. A dot B cross C is the volume. Well, here is the direction of B cross C. And this vector carries the area of this parallelogram. If A is in the same direction as this, what I'm basically doing is I'm building up basically a very nice region. If, however, A is in the same plane as B cross C, then what would be the volume? If A happens to live in the same plane as B and C, what would the volume be? 0. My region no longer has any height. So in fact, all that really matters is essentially how much of A is in the direction of the normal to this, to the parallelogram. And that's where the dot product comes in. So it's going to tell us how much of A do we have in this direction. So if A happens to be in the same direction as B cross C, nothing is lost. As A has less and less and less of its direction in the same direction as B cross C, then my volume should be getting small and small and small. The height is going down. Okay? So this is a beautiful formula. It has a lot of nice geometric interpretation. We're not going to do too much with the cross product until towards the end of the semester when we get to the big generalizations of the fundamental theorem of calculus. So you should know the fundamental theorem of calculus. It's one of the biggest results in Calc 1, Calc 2, depending on when they prove it. We're going to look at massive generalizations as the semester ends. One of the reasons we're going so quickly right now is so that we'll have time at the end of the semester to really think about and absorb the ideas that are going on in this massive generalization. Okay, any questions on properties of the cross product? Okay, so now it's time to do equations of the line. So before we do anything in multivariable calculus, what's our default option? What do we do first? Algebra. Well, which algebra do we do? I'm sorry? Yeah, so before we do something in higher dimensions, we do something in lower dimensions. We always go back and see, have we seen anything like this before, and how should we generalize it? The difficulty is it's not always clear how things generalize. And we'll see later today that a concept you've had from somewhere between 7th grade and 10th grade doesn't generalize immediately. But you are actually working with vectors somewhere between 7th and 10th grades. Your teachers just never told you. They basically hid it. And so my job today is to unhide it. So this is now section 11.4. Equations of lines and planes. So let's review. There's lots of different ways of writing equations of lines. Basically, depending on what information I give you, there are different ways of writing down the equation of a line. So does anybody know a way to get an equation of a line from certain information? You get to choose what information. I'm sorry? mx plus b. So this is the slope-intercept. So I give you the slope m, the intercept b, and the equation is y is mx plus b. And when x equals 0, you get y equals b. So this tells you where the line hits the y-axis. And then you go over 1 unit here, up m units there. Okay, so this is the slope-intercept. What other ways do we have to get the equation of a line? Yes? Point slope. My personal favorite. So I give you a point P. Maybe it's, you probably write it as x naught, y naught back in Algebra 1. I give you a slope m, and then the line is y minus y naught is m x minus x naught. So this is the equation of a line going through the point x naught, y naught with a fixed slope. There's one other way to get the equation of a line. So I've given you slope-intercept, I've given you point slope. There's one other pair of information I can give you. Yes? 2 points, excellent. So I could give you P is x naught, y naught, q is x1, y1. And the way I find the equation of the line is I do a standard mathematical trick. I reduce to something I already know how to do. So from this, I can calculate the slope. Calculate slope. And you get m is y1 minus y0 over x1 minus x0. And now use point slope. So we can actually reduce, if we're given point, point, we can actually reduce back to the case of point slope. Okay. What I want to do now is I want to show you a way of re-looking at what we've done that's going to be more illuminating for higher dimensions. There is a vector going on in this problem. So we're going to reinterpret. Okay. So we were supposed to have a video today. I was going to move up the Tron video to today, but since the projector wasn't working, I want to keep you in sync with the other class. And I think it would be very unfair if you watch a movie while they have a lecture outside in the snow. So if there was more snow, it would have been different, but it wasn't enough to do anything. So let's think about what's going on. So here's my point P, x0, y0. And I want some line going through this point. What does it mean to have slope m? So can someone tell me, what does it mean to say a line has slope m? Yes?
For every additional unit of x,
Good.
you add a certain number of y.
Good. So if I go over 1 unit in x, I go up m units in y. So slope m means if x changes by 1, then y changes by m. Turns out there's a vector lurking here. The vector is v is the vector 1m. So over here, this is the vector v is the vector 1m. And what it's telling me is I start off at the point P. So here's my origin. Here's my vector P. And I want to look at all points, Q equals x, y, z that are on this line. I want to be on a line going through this point with a given slope. That's the same as starting here and moving in that direction v. So, oops, sorry, this is 2 dimensions. So I would have q minus p is a multiple of v. So I would get xy minus x0, y0 is a multiple of v. So let's call that multiple t. Ideally, of course, you'd use the letter m for multiple, but m is taken in these problems for slope. So we're going to use the letter t. It turns out we can now immediately rederive our old equations. So let's give a value to the point. Let's call this point maybe the point 2, 4. So we get xy minus 2, 4 is t times 1, 3, or just expanding everything out, x minus 2, y minus 4 is t, 3t. So this is one way of writing the equation of the line, but it may not be clear that this is exactly what we've had before. Well, let's think about what's going on. The first part, when that equals t, the second part equals 3t. So the second part is 3 times the first. So this means y minus 4 is just 3 times x minus t. Oh, well, that's basically the equation of a line going through the point 2, 4 with slope 3. So this recovers point slope. So we get back to point slope. We can expand out what we have. So we have x minus 2, y minus 4 is equal to t 3t. So this is really two equations. This is x minus 2 is t. This is y minus 4 is 3t. So I can write this as x equals 2 plus t, y equals 4 plus 3t. So this is one way to write what we have. I actually prefer to be a little bit more explicit. I prefer to write x of t is 2 plus t, and y of t is 4 plus 3t. So why is it better to do this? Why is it better to use some extra chalk and write x of t, y of t? So again, always know the reason behind what you're doing. Always know the reason behind notation. I'm trying to highlight something. I'm trying to emphasize something by writing x of t. I'm trying to, yes?
Well, is it so that you're working in the same variables?
Basically, yes, is that I want you to think of x and y as they're functions of the same variable. You give me a time, and this will give you your coordinates. So at any moment in time, I know where I am. And so x and y are really functions of this new parameter. So this is called parametrizing the curve, or parametrizing the line. So how many dimensions is a line? A line is a what dimensional object? Sorry? One. I just couldn't hear over the clapping. They liked your answer. It's a one-dimensional object. So I should have just one variable that's needed to tell me where I am on the line. So I can write, L of t is x of t, y of t is 2 plus t, 4 plus 3t. And I can check, is there any value of t where it would be pretty easy to check and see if it's reasonable? What values of t should I try? 1. Okay, that's the second one to try. There's a more natural one than 1. I'm sorry? More natural than minus 1. 0, right? Always do nothing first. Check the 0 first. If I take 0, I should get back my point P. If t equals 0, we get 2, 4, which is just our point P. And then if t equals 1, we now get 3, 7, which is P plus V. So both of these checks are reasonable. And so, what information do we know? Well, we want a line going through the point P in the direction V, in the direction 1, 3. And so we can check and see, well, when t equals 0, are we there? Yes. When t equals 1, we should have moved one copy of V, and we have. So this is a reasonable description of a line. Now, everything I did here was in 2 dimensions. Could I have added another component? Yeah, the argument would run exactly the same. All that would change is I now have x, y, z, x naught, y naught, z naught. The argument would be identical. It's I start at a point, I choose a direction, and the line is going to be all things of that form. So the general situation is now in 11.4. So equations of lines. So the general situation is I give you a point, and I give you a direction, and the line is going to be all points q such that q minus p is in that direction. So line through p in the direction of q, in the direction v is p plus tv. Now we see how things generalize from before. So in Algebra 1, you talk about the slope of a line. We can't really talk about the slope of a vector in 3-dimensional space. If I give you the vector 1, 2, 8, this has 3 components. See, there's a nice trick we can do in 1 dimension. In 1 dimension, when I'm trying to calculate the slope, I can always have x move over 1 unit and then see how much y changes. So the vector 1, 3, I can just associate the ratio of components, 3 over 1, and call that the slope. So in the standard Algebra 1 case, instead of talking about a vector, we can actually kind of cheat a little bit and talk about this number, this slope. In higher dimensions, we can't talk about slope anymore, but we can talk about the direction. And so this is how things generalize. And so now I give you some vector v. This is the line through P in the direction v. Okay. Any questions on what we've done so far? Okay. So what I want to do now is I want to do 2 examples of just calculating equations of lines, just to make sure everything is good. And just so I use the same example as in 10 o'clock. So example. So let's let P be the vector 1, 2, 3, and V is the vector 0, 1, negative 1. And over here I'm going to take P is the vector 1, 2, 3, and Q will be the vector, I think, 1, 4, 1. Okay. So I want to calculate the equation of the line in these 2 cases. All right, let's see what we have. So L of t is just P plus T times V. Okay. So we get L of t is 1, 2, 3 plus T, and my vector V is just 0, 1, negative 1. So I get x of t, y of t, z of t is going to be 1, 2 plus t, 3 minus t. So this is the equation of the line. It goes through the point P in the direction of V. So if you want, here's the origin over here. Here's my vector P. Here's the vector V. And this will be the equation of the line. Okay. Any questions on how we got the equation of the line in this framework? Yes? Okay, so so imagine you have some point here, Q, which is on the line. Then Q minus P has to be a multiple of V. So if my point Q is my point x, y, z, then I need x, y, z minus P has to be some multiple of V. I'm moving in the direction V from the point P. And then just rewriting, this becomes the same as x, y, z is just P plus TV. So this is the equation of a line. Here's my base point, my anchor point, here's the direction I'm moving, and here's how much I've moved, how many copies of V I've moved. You could have different anchor points for a line, and it'll still be the same line. Okay, let's look at the other case. So I gave you 2 points here. I gave you P and Q. So what would you like to do? How would we handle this case? Perfect. So right next to going from point, right? We basically mirror what we did in Algebra 1. I want to find the direction because I know if you give me a base point and a direction, I can write down the equation of a line. I have a base point, I have P, I want to go through the point P, but I don't have a direction. Well, I can calculate the direction by using my point Q. And so if I use that, if I look at the difference between Q and P, that will give me some vector. I don't want to call that vector V. Why don't I want to call that vector V? Yes?
V is only one, that's longer than right? It's like a unit vector sort of?
Well, this vector wasn't necessarily a unit vector before. So V doesn't have to be a unit vector. We'll talk about unit vectors later. We actually don't need to have unit vectors in anything we're doing. The reason I don't want to use the letter V is I've already got V being used on this board right now. v is the vector 0, 1, minus 1. I don't want to overload notation. I took a class once with a professor, since this is being recorded, I won't say who actually had the letter f meaning different things depending on whether or not it was on the left or the right-hand side of the equation. And so the f on the left was not the same as the f on the right. And this was not pleasant. Okay? You want to be very careful about notation. I'm going to use the letter w. So w is q minus p. It's going to be 0, 4 minus 2 is 2, 1 minus 3 is negative 2. So I want to find the equation of the line. So the equation of the line, I'll use a capital L. I'm going to use the variable s rather than the variable t. I always hate having to use s's in class because s's can look a lot like 5s. So I'll try to put little lines around the s. It's going to be my base point plus some multiple of my direction. So I'll call it a of s, b of s, c of s, my three components, is going to be p, 1, 2, 3, plus s times this vector 0, 2, minus 2. So I get 1, 2 plus 2s, and then 3 minus 2s. Okay, so we now have two lines on the board. The natural question is, are these the same lines or are they different lines? What do you think? Same or different? Do they look different? I think they look a little bit different. Can you give me any point that's on both?
Well, are they parallel?
Well, let's see. If you can give me a point on both, we know that not only are they parallel, but then they're the same. So can you find any point on both of these lines?
1, 0, 0.
Well, there's a really good candidate point that's on both of them. When you look at this, yes? Yeah, p. The point 1, 2, 3 is on both of them. If I take t equals 0, I get the point 1, 2, 3. If I take s equals 0, I get the point 1, 2, 3. Both of these lines go through the point P. So if you think what's going on, here's 0. Here's the point P. The first line is the line going through point P in the direction 0, 1, minus 1. The second one is the line going through point P in the direction 0, 2, minus 2. Ah. What's the relation between these two vectors? Well, we can't quite say the same stuff, so we have to say the same direction, right? 0, 2, minus 2 and 0, 1, minus 1, they're in the same direction. They actually generate the same line because we start off at the same point and we move in the same direction. The correspondence is let t equal 2s. And so if s equals 5, that corresponds to taking t equals 10. So we're hitting all the same points. We've just parametrized time differently. So we have a Canadian visiting us almost meters versus feet, right? I think one of the only places the English and the metric units agree with is seconds. But think of it as just reparametrizing the units you're using. Here you're essentially going twice as fast. If s equals 1, 1 second down the line, you've already moved 0, 2, minus 2. Whereas here you've only moved half of that. Okay? So they're the same line. This is a common feature in mathematics. The same quantity can be represented many different ways. Okay. This basically completes the discussion on lines, equations of lines. Any questions on what we've done through here? Okay, so the next is after lines comes, what should come next? I'm sorry? Planes, right? The other natural thing you could say is curves, more complicated paths in space. We'll actually talk about planes. So if I give you a plane is a two-dimensional object. So what I have now is I have two different directions. Well, actually, in some sense, I have infinitely many directions I can move. But I have to stay within a certain realm of directions. And so we're going to see a way now to write down the equation of a plane. The plane is going to be extremely important to us. In one variable calculus, the equation of a line is important because the tangent to the curve gives you the instantaneous rate of change. And you can use that to approximate the function. In several variables, the plane is actually going to allow us to approximate a function of several variables. Or more generally, a hyperplane will allow us to approximate a function of many, many variables. All right. So as a Bostonian, what is the one thing I like about New York City? The grid, yes. I think there's a Lego exhibit coming in the near future, which I will also like. But for the most part, so the grid system is wonderful. Okay? If you go to Boston, you will really appreciate the grid system. So imagine this is I hat, this is I, this is j. And if I give you any vector xy, I can write it as x times I plus y times j. So I can represent any point in the plane as some number of copies of I plus some number of copies of j. What if we used a different coordinate system? What if we used different vectors? What if we used the vector v is 1, 0, and the vector w, which is the vector 1, 1? Is it still possible to write every vector in the plane as a combination of v and w? And again, to do the subject justice, you'll really want to use what? Linear algebra, right? So we're going to basically do the very quick, just what we need from linear algebra to survive. So imagine I give you some point xy, and I want to say it's some number of copies of v plus some number of copies of w. Well, this gives me, xy is going to be t0 plus ss. So we get xy is t plus s times s. So x is t plus s, and y is s. Which equation is easier to solve, x or y? So I want to express y. So I'm trying to find s and t in terms of x and y. Y equals s is very easy. I can just flip it. And I get, oh, okay, s equals y. Then x equals t plus s becomes x equals t plus y. So t is x minus y. So I can express anything, any vector xy, as some number of multiples of v plus some number of multiples of w. More generally, I want to consider two arbitrary vectors v and w that are not aligned. And so what I really need to do is I need to consider v like this and w like this. Okay? To do this properly requires linear algebra. I'd have to write down the coordinates of v, I'd have to write down the coordinates of w, I'd have to then show I can represent an arbitrary point xy as a combination of this. I don't want to do the full proof, I want to give you a more relaxed version of the proof. Basically, it's proof by reclining. Okay, we've seen this before. Basically, all I have to do is just recline back like this. Equivalently, pick up the entire universe and just tilt it backwards a little bit. So just rotate this whole thing a little bit so that v is now pointing in this direction. And so, I preserve the angle. Well, if I just rotate it back like this, it's not so bad. You give me a point xy now, what I do is I take enough copies of w to get to the right y height. And now I just take enough copies of v to just correct and move back. Okay? So you can really generalize this argument. You can draw it, you have some point like this. You can just change your coordinate axis. Linear algebra is really good at helping you change your perspective like this. But this is a rough idea that as long as v and w are in different directions, then any combination of them, so then all the different combinations of them will give you the entire plane. Okay, so now we have some idea of what is a plane, and how many dimensions does a plane have? It's how many dimensions? 2. So we had one free parameter for a line. we had our parameter t. So for a plane, we're expecting two free parameters, maybe a t and an s. And so you'll have to give me two pieces of information to tell me where you are in the plane. Well, that makes sense. A plane is 2 dimensions. It's a little bit more complicated. So now, equation of planes. So the plane through the point P with directions v and w is the following. So again, as always, here's the origin. Here's P. Here's my plane. And here are my directions v and w. So I want all points Q such that Q minus P is a combination of v and w. Okay. So what would that mean? That would mean Q is P plus some number of copies of v plus some number of copies of w. And this is one way of writing the equation of a plane. Right? Here's my point, and here are my two different directions. And you can see that if you subtract, you get Q minus P is some multiple of v plus some multiple of w. So this is the equation of a plane. So I have to give you now three pieces of information. The anchor point, the base point, and two directions. I can, of course, change my base point, and as I change my base point, the equation is going to look a little bit different, but it's still going to be the same thing. Okay, so now if I give you, P, V, and W, you can write down the equation of a plane. It turns out there are other ways to write down equations of planes. And so let's go back to the case where we have, a plane here. And now I have some vector in the plane. So here's P is to here, Q is to here, Q minus P is this vector here that's in the plane. Each plane has a unique direction coming out of it. It's called the normal to the plane. Another way of looking at the plane is it's all points that are perpendicular to this normal direction. So how many directions do we have in three-dimensional space? 3, right? We lose one direction for the normal. We're left with two directions. Exactly the number of dimensions for the plane. So another way of looking at this is to use normals. And so here's 0, here's our vector P, here's V, here's W, here's our plane, and with really good imagination, there's our normal vector. And I want all things that are perpendicular to the normal vector anchored at P. So what this means is, here's some other point Q, and then I need Q minus P to be perpendicular to N. All right. Is there any way to figure out when two vectors are perpendicular? Yes. When the dot product is 0. Beautiful. Right? We can now milk all these different facts we have. There's a nice geometric interpretation. So we need Q minus P dotted with N to equal 0. So we get Q dotted with N minus P dotted with N is 0. Or Q dotted with N equals P dotted with N. So there's a couple things to note here. The first is this 0 the number or is 0 the vector? 0 the number. Whenever you take the dot product of two vectors, you get back a number. So this should be 0 the number. If I multiply the normal by 5, if I rescale it by a factor of 5, does it affect the dot product being 0? So if I multiply every component of the normal by 5, is the dot product still going to be 0? Yeah. I've multiplied this part by 5, I multiplied this part by 5. These two are still going to be equal to each other. I don't have to take the normal to be unit length. I can if I want to, but I probably don't want to. I want to just take any normal that works. So for example, if the normal is ABC, then if P is P1, P2, P3, then the equation of the plane through P and having normal n is just the following. So it would just be Q dot n. So Q dot ABC equals P1, P2, P3 dot ABC. And so if we write our general point Q as x, y, z, we get ax plus by plus cz equals, I'll write it this way, AP1 plus BP2 plus CP3. Does it matter that I'm writing AP1 as opposed to P1A? No. The convention is just normally you write the earlier letter in the alphabet first. So this equation has a lot of nice features about it. We see that if I multiply all of A, B, and C by 5, it's still going to be true. The other thing is, once you fix x and y, once you choose values for x and y, we have CZ is AP1 plus BP2 plus CP3 minus AX minus BY. So once you choose x and y, z is forced. So choose x and y, then z is forced. We have two free parameters. Do you expect to have two free parameters for a plane? Yeah. What dimensional object is a plane? 2. If you're trying to describe where you are in Manhattan, so many blocks east-west, so many blocks north-south. I expect to need 2 parameters to describe where I am. So when we wrote it all the way over here as P plus TV plus SW, the 2 parameters were T and S. They told us how many copies of V, how many copies of W. This is another way of writing it, and in this way of writing it, you don't really see the directions V and W. What's nice about this is you have infinitely many choices for V and W. I can have V and W like this, like this, like this, like this, like this, like this. I have lots of choices. So what's nice about this is it basically says, screw that, I'm not going to look for V's and W's. There are infinitely many pairs I can choose. What really matters is the normal direction. I want to talk about being perpendicular to the normal direction. So we have about a minute, maybe 2 minutes left. Just enough time for one last way of writing down the equation of a plane. If I give you 2 vectors v and w, do you know any way to find a vector perpendicular to v and w? The cross product, right? There's a reason we started the class with that. So we can use the cross product to get the equation of a plane. So cross product to the rescue. Any formula that's this nasty has to have some good to it, or we would never do it. So we already saw geometrically it's useful. It tells us the area of the parallelogram. We can also use it to calculate equations of planes. And we're going to use planes to approximate complicated functions. So this is going to be very useful. So if this is V, if this is W, as always, this is my point P, here's the origin, here's my plane. I can take as a normal direction the vector V cross W. What if I did W cross V? What would happen to the normal? It now point downward. But that's fine. That's just multiplying through by -1. That's not going to change the equation of the plane. You'll still get the same plane. So if you want to calculate an equation for the plane, one very simple way, if you want to use this ABC formula, is to just use this normal vector. Now, we often put a hat on something to indicate unit length. I could divide this vector by its length, and now this has unit length. There's no need to do this. It's sometimes convenient and nice to have unit length vectors. There are some formulas where you have to divide by the lengths of vectors. So if your vectors always have length 1, you never have to worry about have you memorized the formula correctly. So for some things, it's not a bad idea to normalize, but in a problem like this, it just makes the algebra more complicated. Okay, so this completes section 11.4. We will do section 11.5 on whatever days comes next. I think it's Monday. There'll be a review session next Friday in class. The Monday after that, first Math 105 exam will be on chapter 11. The applications of math lunch will be today at noon in Mission. So far on the agenda is talking about like math and baseball, but anything you guys want to talk about how math can be applied is fair game. There are no review sessions tonight and Saturday. I have no idea why there are no review sessions on Friday and Saturday nights, but if you do have any questions as you're doing your homework, feel free to shoot me an email and I will respond to email.